I wanted to start before I kind of get back on firmer ground, for me at least, to finish an IOU from yesterday. So yesterday we talked about these four-dimensional gauge theory, particular this n equals 4 super Young-Mills, and one of the main features of these theories that we need to comment on is what are the observable in these theories? What are the operators? The operators that we can actually calculate in these theories, and how do they match up with the Langlands program? So I just want to make a couple of comments on this before changing gears kind of drastically. So the operators in these four-dimensional gauge theories come in two types. Well, the basic operators. So we're going to look at a specific kind, which are the line operators. So line operators are given. First of all, we're going to take a line. So we take a one-dimensional submanifold of our four-manifold. So I don't know. Actually, this was a all right, something like that. So we take a loop inside of our four-manifold, and we can assign to this loop two kinds of observables. So the first kind are called the Wilson loops, and the Wilson loops are given as follows. So we have we're looking at a gauge theory, and with the gauge group is G, or rather its compact form. And so we pick if we pick V a representation of the group G, then we can make the following calculation. It is for any connection. So we're looking at some gauge connections. So A is our gauge field, which is a connection. We can assign to it the holonomy of the connection A along L in the representation V. So we take the associated vector bundle, take the representation, associated vector bundle in representation V, take the holonomy, and take its trace. So this is something we can calculate classically for a connection. For every time you give me a loop and you give me a representation. And this gives me an operator in the quantum field theory, which is a kind of known as an order operator. This is a kind of operator which we can stick into the path integral. So we have this integral over all the fields phi, d phi e to the minus s of phi, and we can just stick in here the Wilson operator associated to the representation V of the connection A, which is part of our field phi. So this gives me something to calculate in the quantum field theory. And so this is one kind of observable labeled by representations of G. The other kind of observable is a little less familiar. These are called 't Hooft loops. And the 't Hooft loops, the way I'm using the explanation of 't Hooft loops that in a paper of Kapustin. So the way we look at 't Hooft loops, rather than looking at the path integral like a typical operator, and rather than sticking in some operator into the path integral and evaluating this, we're going to change the space of fields over which we take the path integral. So the things we're going to calculate are now going to be integrals over different spaces of fields. So what do? We take this, we take our gauge field and we take our loop, and we're going to look at connections with a singularity of a prescribed kind, with a singularity along the loop. So rather than taking our path integral over the space of all connections, we're going to do an integral of e to the minus s of phi d phi. We're going to take the same kind of integral, but over a new space of fields where these fields are required to have a particular kind of singularity. So this is a different kind. This is an example of what's called a disorder operator. And so you can ask what kind of singularities does it make sense to ask? So what are these singularities labeled by? And there are several ways to say this. In the abelian case, there's a classical example of such a singularity, which is the Dirac monopole. So I'm not going to explain exactly what the Dirac monopole, but one way to say what these singularities are is just to say that you take, if you give me a co-character, nu from U1 into G, so you give a homomorphism from U1 into my group, I can take my standard model of a singular U1 connection, which is called the Dirac monopole, and I can induce from it a singular G connection. It induces a particular kind of singularity along this loop. So this is an example of a magnetic monopole. We think of this as being our time direction. And this is our space slice, and this is a monopole at this point. So moving in time. So you can induce particular kinds of singularities labeled by co-characters. So we've seen co-characters appeared when we tried to describe the affine Grassmannian. We can also say the same data. Let me say the same data in a slightly different way, which is that if you try to ask what are the possible singularities, so I'm going to look at my loop L close up, and I'm going to say, how am I going to describe a singularity of a gauge fields on loop L? Well, I'm going to look in the transverse direction to the loop. So I have a little two-sphere. Here in this is supposed to be a four-dimensional picture. I have a little two-sphere linking my loop, and I can look. The way I'm going to describe the types of singularities of my gauge fields on this loop is by saying, what do they look like? I'm going to assume that it's kind of a conical singularity, so near the loop. So it's described by what it does, what the gauge field looks like on an S2. So the possible singularities are given by solutions of Yang-Mills on S2. So what you find is that the possible singularities are given by, after translating from Yang-Mills equations to bundles, these are exactly given by holomorphic G bundles on P1. These are given by points of holomorphic G bundles on P1, which are labeled by representations of the Langlands dual group. So this is the fundamental data. You can either think of this as giving a co-character up to conjugacy. So this will mean an element of the co-character lattice up to W, which we explained is the same as the lattice of representation, the same as irreducible representations of the dual group. This is an irreducible representation of the dual group. Or we could just do the same calculation again here, that this is our double coset space, and these double cosets are labeled by co-characters. So the basic observation is that kind of magnetic monopoles, singularities, are labeled by representations of the dual group. So for every representation V check, an irreducible representation of the dual group, we get an operator, which is the 't Hooft operator, labeled by V check, and corresponding to the line L. So here, I guess I should call this is WVL. So there's an operator, WVL, associated to a representation of G and a line, and they have a similar operator in the same gauge theory, but now labeled by representations of the dual group. And one of the fundamental properties of the S duality, if you'd like, how we derived the geometric Langlands conjecture from looking at the structure of Hecke operators, you can also try to, where does the S duality come from? It comes from trying to exchange electric and magnetic fields. And here I'm going to think of it as something that exchanges these electric and magnetic observables in the theory. So one of the fundamental properties that you expect from S duality is that it exchanges Wilson and 't Hooft loops when we go from the group G to the group G dual. So this is already manifestation. So this is already suggests something that looks a lot like geometric Langlands, in that we're seeing that there are operators labeled by representations of the dual group. And let me just maybe make a kind of a more formal comment, which is that we remember that our geometric Langlands categories are Hecke the Hecke operators, the way we describe them in this topological field theory picture, the way we got them was by looking at our theory, ZG0, so on the two-sphere. So why does the theory on the two-sphere have to do with these loop operators? So if I give you a loop in 4 dimensions, so how do I think of this loop operator acting? Where do these operators act? Well, this is the same picture as we did for point operators. We take this is a 3-manifold, and the Z of the 3-manifold is the space of states of my theory. I look at the 3-manifold cross time. I cut out this loop, and the possible operators that I can stick here are given by you cut out the loop and look at its tubular neighborhood. And so now we have a diagram that goes from this is an action of Z of the tubular neighborhood acts on Z of the 3-manifold. So these are how these loop operators give operators. But this tubular neighborhood is just S2 cross S1. So you can ask, what is Z of S2 cross S1? And there's a general kind of yoga in topological field theory that tells you what happens when you cross by a circle. Crossing by a circle is supposed to be some kind of trace. So this is supposed to be some kind of trace of Z of S2. In this categorical context, the trace is given by something like Hochschild homology, or we could just say K-theory. So the K-theory of Z G0 of S2 is what you expect to give the loop operators. So ZG0 of S2, this is the category of representations of the dual group. And now we have the loop operators are given by its K group, in other words, just by the group ring, by the representation ring of G dual. So that's how we can see why, from this topological field theory picture, why we might expect this. So what have we done? We're going from a 4-dimensional picture, we're going down to 2 dimensions. And so we think of, here's my 2-dimensional surface, and I'm looking at C cross sigma. So this is my 4-dimensional space. And so before instead of looking at loop operators in 4 dimensions, I'm going to end up looking at point operators in my 2-dimensional picture. Okay, so this is just a schematic way of saying how Kapustin and Witten derive the relation between Hecke operators and 't-Hooft loops. So they say in the 4-dimensional theory we have these operators given by 't-Hooft loops, and we're going to try to see what happens when we go down to 2 dimensions. How do these things act on branes? And when you work out what these things act on branes, they show exactly that you get the Hecke operators. So maybe I should say one thing very nice that comes out of this picture, the way we explained Hecke operators was a kind of a very static point of view. We look with a G bundle, and there's this kind of correspondence over the space of G bundles where you look at all ways to modify a G bundle at a point. So the picture that arises of Hecke operators from Kapustin and Witten is a very kind of dynamic picture. So I give you my Riemann surface. So this is my Riemann surface C. And I have a point. And I want to see how do I do a Hecke modification of bundles at this point. So what Kapustin and Witten say, well, let's let some time evolve. We now have a 3-manifold, C cross an interval. And now we're going to look at space of solutions of the Bogomolny equations. So these are the monopole equations. These are the 3-dimensional equations coming from reduction of the 4-dimensional theory. So this is kind of the 3-dimensional version of Hitchin's equations in 2 dimension, Bogomolny equations. So we look at solutions of the Bogomolny equations. And what the Bogomolny equations basically say in this setting, they just say that if you have a holomorphic bundle, you don't want its holomorphic type to change. If I give you just a solution of the Bogomolny equation where I start with a holomorphic connection defining holomorphic bundle here, what the Bogomolny equations are saying is that I don't want that the holomorphic type of the bundle is not changing. So that just means that nothing is happening to my connection, to my bundle. But now I'm going to look at solutions of it with a singularity at a particular point. So they study solutions of the Bogomolny equations with a singularity at a particular point, which we should think of as part of a line operator in 4 dimensions. This is passing through this 3-dimensional slice. We have a singularity of our connection, which is kind of crossing this monopole line. And so now the Hecke modification happens in a dynamic way. You start with your bundle, you flow it along, you hit a singularity, and you come out as a different bundle in the other end. So they describe Hecke correspondences as the Hecke correspondences are given by spaces of singular solutions of the Bogomolny equations. So solutions of the Bogomolny equations on your Riemann surface cross time with a particular singularity. And if you remember, this is exactly the picture we said how in a topological field theory, why the two-sphere, why the theory assigned to the two-sphere acts on the theory assigned to any surface. Okay, so, and questions? Okay. So I'd like to now change gears completely. So we take a deep breath. Okay. So now, right, so no more physics. And I'd like to talk about representation theory. So now I'd like to talk about how the geometric Langlands program interacts with some problems in representation theory. So we've already seen a beautiful explanation of this in Ruminen's lectures of some aspects, and I want to talk about some other aspects. So let me just sort of outline what I'd like to do, and then you'll see how absurd it is for the amount of time. So I'd like to review some properties, some pictures in geometric representation theory. After which I'd like to say something about the role of representations of loop groups, how representation theory of loop groups relates to the local version of geometric Langlands. And then I switch pen. And so here I'm going to describe some ideas of Beilinson-Bernstein and Frenkel-Gatesgory. After which, and I'm also trying to explain how, maybe I'll just put in context that if you're feeling very brave and want to do topological field theory with 4 tiers, if you're willing to go 4 tiers, you're going to get something related to this. So this is from the point of view of topological field theory, we're going to go now not to surfaces, but to the circle. But since 3 tiers is already a little much, I won't say it in that way. And then I'll talk about the special setting of tamely ramified Satake correspondence, which is work of Bezrukavnikov. And finally, hopefully, I'd like to get to representation theory of real Lie groups. So I have to see how all of these ideas might apply to study representations of real finite dimensional Lie groups. This is work with David Nadler. Okay, so that's kind of the outline. So let me start by saying a few words about representation theory of finite dimensional Lie groups, and trying to put it in a language where it might interact with some of the structures we've seen. So okay, so this is if I believe number 4 of the motivations for D modules that I said all the way on the first day. Where do D modules come from for representation theorists? They come from this construction of Beilinson-Bernstein. This is the main motivation to study D modules for representation theorists. So Beilinson-Bernstein localization theory has the following. First of all, the rough schematic form we already said that if I have so here G is going to be say, finite dimensional reductive complex group. So just one of our favorite groups. It's acting on a variety X. What you get out of this automatically is a map from the enveloping algebra of G to differential operators on X, to global differential operators on X. This just comes from differentiating action. The Lie algebra maps to vector fields, and the enveloping algebra then maps to differential operators on X. So as a result of this, you get adjoint functors that Dmitry explained from representations of the Lie algebra. So by here I mean vector spaces in action of the Lie algebra, not necessarily finite dimensional. So we get adjoint functors between representations of the Lie algebra and D modules on X. And these functors are basically tensor and global section. So one functor, so let's call them delta and gamma. So gamma is just gamma. If I take global sections of a D module, it has an action of global sections of D. And inside of there is UG. So the more interesting one is the localization functor, which is really a non-commutative analog of the just usual localization for modules over a commutative ring. And that says if I give you a representation of G, then I'm going to just take this representation and maybe I want to do it on the other side. I don't know. I'm going to take the ring of differential operators on X and tensor it with M, imposing the relations from UG. So UG gives me some global differential operators. So I just take a free module generated by M and then impose on it the equations that cut out M. Okay, so this is the functor. So it's a natural functor, and what's the miracle discovered by Beilinson-Bernstein is that in nice cases this functor is almost an equivalence. So as Ruminin explained, there's a notion of being D affine, which is a very nice context of varieties for which D modules on X are taken to global sections of D modules where this is an equivalence, where the functor of taking global sections in equivalence, these are called D affine, and it turns out there are actually a lot of interesting spaces, including flag varieties, which have this property. So what's the idea? We're going to take for our space X something very special. We're going to take the flag variety of G. So here G is a reductive group and B is a Borel subgroup. So in GLN this is upper triangular matrices. And so I look at the flag variety, which is in GLN is this set of all flags, full flags of subspaces in Cn. And this is going to be the X I'm going to take. The G is going to be the action of G. And why do I expect this to be a good place? Partly because I know the Borel-Weil theorem. So the Borel-Weil theorem tells me that irreducible representations, irreducible finite dimensional representations of the group G, they all appear as global sections of L for L some unique defined holomorphic line bundle on the flag variety. So Borel-Weil already told me that if I'm interested in irreducible representations of the group G, I can get them by studying line bundles. This is not quite where I want to be yet because these line bundles are not D modules. These line bundles are not flat. They have curvature. They have a non-zero Chern class. So really, if I wanted to think of these as something like D modules, I'd need to introduce D modules with a little bit of curvature. So these are called twisted D modules. So I'm going to ignore the subtlety of twisting of the D modules and infinitesimal characters. But we're still going to use this Borel-Weil theorem as a motivation. And what this motivation leads to is the theorem of Beilinson-Bernstein, which says that this localization functors on the flag variety give an equivalence between differential operators on G mod B modules and modules over the global section of differential operators on G mod B. And moreover, these global sections of differential operator G mod B is, let me call this UG0. So this is a quotient. I don't get the full enveloping algebra of G. I get the quotient by some central ideal. And this ideal somehow tells me that I want to look at the zero curvature rather than looking at some other curvature. So a better way to say that this is the same as representations of the Lie algebra G on which I put some central character condition. So we can get rid of this zero by being a little more clever with what we put here by putting some central curvature versions. So I'm going to ignore that from now on. I'm just going to think of representations of the Lie algebra as being given by D modules on the flag variety. Okay, so the Beilinson-Bernstein theorem now allows us to interpret everything that we can say in representation theory of Lie algebras in terms of geometry of flag manifolds. So what do we do with this? So where do we get why do we care about representations of the Lie algebra? So the interesting categories of representations of Lie algebra, they come from what are we interested in? So interesting representations of the Lie algebra. These are the representations that are these are called Harish-Chandra modules. So we don't want to look at arbitrary representations of this Lie algebra. We want to look at ones that integrate to some group. We want to introduce some Lie group into the picture. So for example, we had before representations of the entire group G. We're going to look at representations which are called GK modules. So these are representations that they integrate. A representation of a Lie algebra, but they integrate to some subgroup K of G. So they have some kind of integrability that the actual group K acts on the representation and the entire Lie algebra G. So these turn out to be the good models for the kind of representations, things like unitary representations of real Lie groups can all be captured in terms of this algebraic story. So let me review a little bit of this. So let's see. Let's do some examples. So one example is I'm going to take K to be the Borel itself. So I'm going to introduce a category, which I'll call HGB. So this is the derived category of D modules. Okay, so I'm going to introduce this thing. So what is this thing? These are D modules on G mod B, which are equivariant for B. They're invariant. Maybe it's better to write it. They're D modules on the flag variety. So in other words, they're representations of the Lie algebra with integrability to the group B. So that's what this notation means, that these are representations of the Lie algebra with an integrability to B. So this is roughly up to these kind of issues that I said I'm ignoring, issues about these infinitesimal characters. These are roughly the same as what's known as the category O of highest weight representations of the Lie algebra. So for people keeping track, these would be, I would have to put some conditions on monodromicity rather than equivariance of B. But so this category appears, this is a category that contains things like Verma modules. This is a category of highest weight representation of the Lie algebra. Or another manifestation of it is this. This is also appears as the category of infinite dimensional representations. These are representations of the group G, but now thought of as a real Lie group. So I'm going to think not of algebraic finite dimensional representations of G, but I'm going to look at representations of G as a real Lie group. This contains infinite dimensional representations like principal series representations of SL2C. So these are the kind of representations I can model by looking at representations of the Lie algebra which have a condition with respect to upper triangular matrices. Okay, so so maybe I should give this, yeah, so, okay. Maybe I'll give this guy also another name. I'll call it Harish-Chandra modules for the complex group, so G sub C. So this is one kind of category of representations that can be studied geometrically using Beilinson-Bernstein. It's given by studying the geometry of B orbits on the flag variety, in other words, Schubert geometry. So another class of representations that I get this way that's of great interest is if I want to replace complex group by real Lie groups. So suppose I want to understand representations of a real Lie groups. So suppose G R is a real form of my group G. So I'm going to think, say, of SL2R inside of SL2C. Then I might be interested in studying the category of representations, category of Harish-Chandra modules. So this is the category of so-called admissible representations of the group GR. And so this contains, for example, all of the unitary representations. So unitary representations of real Lie groups are things that sit inside of this category. And this category has a geometric description, thanks to the Beilinson-Bernstein picture. So I'm going to state it not in the Beilinson-Bernstein form, but what this says is that we're going to look at D modules on G mod B, but instead of putting the condition that they are constant along the B orbits, we're going to put a condition that they're constant along the GR orbits. So this statement is actually not exactly how Beilinson-Bernstein formulated. This is a theorem of Kashiwara and Schmidt. But I'm going to think of this as the same kind of statement. You have to be a little careful technically what do you mean by this, because these are now orbits of a real group. But there's still finitely many orbits of this group, and I'm going to think of this as representations of the Lie algebra with a kind of constancy or integrability to this real group. Okay, so so the
equivalence of categories?
This is an equivalence of derived categories. So I really here I've kind of this is actually by HC I actually mean that this should be the derived category. So Beilinson-Bernstein point of view would be to say not to look at the GR orbits, but to rather look at the KC orbits, which is the complexification of the maximal compact of GR. This is a different group who, if you replace this by this, then you get some geometry that you're happier with. But there's a version of this that's due to Kashiwara and Schmidt, which enables me to look at these. So the claim is that the derived category of representations of Harish-Chandra modules for this real Lie group are given by this category of D modules.
So we're looking at complexes in Harish-Chandra modules.
That's right.
Are they bounded or unbounded?
Yeah, I should probably put bounded. Yeah,
bounded in both directions?
Bounded in both directions. Yeah.
Harish-Chandra modules.
That's right.
Okay.
That's right. The Beilinson-Bernstein picture doesn't require derived. As Ruminen explained, we can do it on the level of abelian categories, but from now on, I'm going to just stick with derived for safety. Okay, so this is a category that we're interested in for a lot of reasons. We would like to understand what the representations of real Lie groups are, and this tells us that it has a geometric description, that we can study representations of real Lie groups in terms of the geometry of orbits on flag varieties. So for example, for SL2R, we can look at SL2R orbits on P1, and the geometry of SL2R orbits on P1 tells us something about the structure of the representations. Well, it tells us, in fact, everything, according to this theorem, about the representations about the Harish-Chandra modules for SL2R. Okay, so what kind of questions are there? So this is a theorem. This gives you a description, so you can ask, what would you like to do? Well, there's a lot of more refined questions that you might try to ask. And the kind of questions you'd like to ask about these representations are given by the kind of formulated in terms of the real local Langlands program. So this is something that grew out of the original Langlands program for number fields. This is the local picture of the Langlands program for number fields at the place R. So we've kind of studiously ignored the number fields picture. But let me just say what are some features of the real local Langlands program. The real local Langlands program wants to describe these representations of the real Lie group. And what kind of ways does it say? So you want to describe representations of a real Lie group. So in terms of Langlands dual data. So in terms of some kind of Galois data. Galois data. So I'll be more specific a little later. So what do I mean by Galois data? First of all, the Galois group here, the relevant Galois group is just Z mod 2, which is the Galois group of the algebraic closure of R. So you want to look in Galois data in the Langlands dual group of G. So you want to give a description of the representations of the group GR in terms of some kind of data that involve conjugacy classes in G dual and involutions. That's the kind of data that you would like. And in fact, this data is, so in fact, you can make some kind of, so let me say a little bit about what's known about this, is that Langlands and Schelsted, there's a description due to Langlands and a refinement due to Langlands, and Schelsted give a description, give a complete description, let me not say of the irreducible representations. So if you look at the irreducible representations in here, they give a description of these irreducible in terms of nice Galois data. So are we done? Well, you can, this is wonderful work based on Harishandra's result, but then you can ask, well, more than studying the irreducibles, there are a lot more refined questions I could ask. So the next kind of thing I can ask is to try to describe the Grundy groups, to describe the K group of representations. So I have this category of representations, and I want to describe the K groups in terms of Galois data. So to be more specific, we can make there's a particular spaces which are Langlands, which are particular Langlands, or they're also known as geometric parameter spaces. And I'm going to give the examples of these at the end if we get there. So these are finite dimensional complex algebraic varieties that are built out of this data, out of Z mod 2 and G check. So I'm not going to say specifically which ones. But so basically the points of these give you irreducibles, and the K, my order got off. So the Vogel described the K groups of representations, described the K groups of the representation in terms of K groups of these Langlands parameter data. So at this point, we have a lot of information. We understand the irreducible representations. We understand the K groups. And I'll give a little more of the flavor of the understanding later. But you can still want to ask, beyond the structure of K groups, you might want to actually understand what the structure of the representations are. So these categories of representations are not semi-simple. There are a lot of interesting extensions. So you might want to understand, how do you describe extensions of representations? How do you describe families of representations? How do you describe the structure of the category of representations? And so for this, there's a beautiful conjecture due to Sorgel, which gives a description, a Langlands dual description of the category of representations. So this is sort of the ultimate part of the real local Langlands program, is to give a description of the category of representations in terms of some Langlands dual data. Okay. So now what structure do we have here? So this is kind of a little overview. So what kind of structure do we have in these categories? So we have the same kind of symmetries, the same kind of patterns that we've been talking about all week. So what we discussed a couple of days ago was Hecke symmetries. And Hecke symmetries are kind of something very general. If we had a space, if you give me a space of the form X mod B, where X is a variety on which G acts, so I'm going to look in the specific case of G and B, then by the general nonsense, we get some correspondences acting on X. Or if you're interested in categories modules, if you look at D modules on X mod B, these will carry an action of a Hecke algebra. And what's the Hecke algebra? The Hecke algebra is the Hecke algebra for G and B, which is exactly D modules on double cosets. This is the algebra, and it acts on these categories. So that's the same Hecke GB that appears on the other board. So the categories of representations, so Beilinson-Bernstein tell us we should just look at X to be G. Look at G mod B, that's the category of all representations. Category of all representations carries an action of this Hecke algebra. And in particular, all of these other categories that I write down, they're all something of the form something mod B. So all of these categories, all of the categories that appear in geometric representation theory this way carry an action of this form. So you might ask, what is this kind of thing? What do these actions mean? So this is something very well known in classical representation theory. These are given by intertwining operators. So these are classical intertwiners between representations. For example, the intertwiners of principal series representations. So that's how we define them. They're given by some kind of integration operators. We write this correspondence. There's a correspondence with G mod B fibers over our space X mod B, and we pull up our function and we integrate. So these are intertwining operators of representations. But more specifically, what does this look like? So the claim is Hecke GB. Well, what does it look like? First of all, to first order, it looks like the finite Weil group. The finite Weil group is in bijection with the set of double cosets. If you look at the set of, these are the Bruja decomposition, the finite Weil group of G looks like these double cosets. So if you're looking at some rough level, if you're looking at something like a level of Grothendieck groups, you're going to see on here an action of the Weil group. So, but we have something, we're not interested just in the sets of irreducible representations, or even in their Grothendieck groups. We're interested in the structure of the category. So what is the structure of this? But what it really is it's a kind of a categorical version. It's a categorical cousin of the Artin braid group. The finite braid group associated to the group, let me call it B sub G associated to G. So what is the braid group? So we think of the finite Weil group. How do you describe the Weil group? The Weil group has generators Si, where I goes from 1 to the rank of G. And these Si have two properties that they satisfy. They satisfy, well, the first property, I should say, is that these Si are involutions. So these are the simple transpositions. In the case of GLN, this is the symmetric group. So I should say maybe this is the symmetric group for GLN. And these are just simple transpositions. And they generate the symmetric group. So we have these involutions. But they also satisfy, if you look at two adjacent involutions, they satisfy a braid relation. Si, Sj, Si, Sj, Si, Sj. And there are similar versions for non-simply laced groups. So you have to say what the version of these relations are. So they're involutions, Si squared equals 1, and they satisfy these braid relations. So what's the braid group? You just drop this. So the braid group says, I'm going to think, so for SLN, I'm going to think that when I permute a bunch of, so I have a bunch of things I'm trying to permute, and when I permute them, I keep track of, I can't really do these, well, let me do something like that. So I'm going to keep track of, did I lose one? Okay, that would not be a good permutation. All right. So the idea is I'm going to keep track of the order in which I switch things. I don't have these S squared is not equal to 1. And there's a similar version for any group G. You can also describe it as the fundamental group. BG also arises as fundamental group of the Cartan, regular part of the Cartan mod the file group. So there's sort of a geometric description of this, but okay. So this is the braid, and so what happens? So the point is this Hecke. If you look at this Hecke algebra, well, we can kind of see these generators SI. So we look at the orbits B mod G mod B, and inside of the flag variety, we have a bunch of smallest orbits, which are a bunch of P1s. These are a bunch of P1s that are labeled by the SI. And we can put a D module on each of these things. And those give me operators, which let's call Ti, are elements of this Hecke algebra. And they satisfy, and the braid relation is something that can be described very geometrically or very topologically. And it's forced to be satisfied. The Ti's satisfy the same braid relations, but they no longer are involutions. So in other words, well, right. So one can, there's a very pretty way to see this structure by, if you don't want to look all the way categorically, you can just, something easier you can do is you try to model, like we did in the Satake case, you can try to model D of B mod G mod B D. You try to model it by looking at functions, by replacing D modules by functions on double cosets, but over some finite field. And this is a great exercise to do in the case of SL2, where this is just P1 over FQ. And you look at functions on P1 over FQ, which are constant on A1 and the point, and you see what happens when you try to convolve them. And what you'll get is you get that these have these generators Ti labeled by the same thing as the Si, and they satisfy the braid relations. But even in this kind of context where you're looking just at functions on this finite set with convolution, you find that they don't satisfy, they are not involutions, but it's at Ti plus 1 times Ti minus Q equals 0. So this gives an involution when Q equals 1. This means that these are involutions. They have eigenvalues plus minus 1. But even when you just look at these things for a number Q, you already see that this involution was something you got lucky with. It's not somehow something that's sort of fundamentally there. So once you go to the categorical world, it goes away. OK, so the point is that all of these categories, so what does it mean to describe, when I say let's try to describe the category? These categories of representations are all categories with an action of the braid group, among other things. So an action of this Hecke GB is some kind of enhanced version. This category is generated in some appropriate sense by a braid group action. So that's what these intertwiners are. So one of our goals in classical representation theory is to describe categories of representations of various kinds, of complex groups, and especially of real groups, with actions of these Hecke operators, in other words, actions of braid groups. OK. Any questions? OK. So now I'd like to go to loop groups. So this is kind of a picture of some of the goals in representation theory, and hope to return to it, trying to address this goal. So what happens in the case of loop groups? Let's try to do the same story in the case of loop groups. So of course, everything is going to get technically more difficult, but the point is going to be, and hopefully when I run out of time, hopefully I'll have expressed the message that going to loop groups, while it seems a lot more difficult in some ways, it is going to introduce a lot more symmetry. And it's symmetry that we can really exploit and actually use to make progress on classical problems. So introducing this loop, in some sense, is going to make a lot of things more commutative. And that's going to be a very powerful tool. So what do I mean by loop group here? I just mean the group G over Laurent series. And so now, how do we study the loop group? I want to study, so we have the loop group and we have the loop algebra, and we have versions of Beilinson-Bernstein results that tell us that representations of the loop algebra are going to be closely related to D modules on appropriate flag type varieties on flag varieties, in particular homogeneous spaces for the loop group. So this is the kind of picture that we expect representation of the loop algebra to have to do with this. Now, I want to say the same words, but from emphasizing the loop group rather than loop algebra. And this is somehow in analogy with the classical Langlands program, which has to do with representations of p-adic groups. So we're going to think this Laurent series in Z replaced as an analog for QP. So, so what do we do in the case of QP? We take our p-adic group and we assign to it its Hecke algebra, which is a version of the group algebra. So that is, I want to assign a kind of group algebra. I can assign a kind of group algebra to the loop group. So this is a slightly scary object, but I want to. So I'm going to think of the loop. Some version of the group algebra of the loop group should be some class of functions on the loop group. So this is going to be something like a category of D modules on the loop group. And I need to put some kind of smoothness hypothesis, and this is going to be some analog of this compactly supported functions. So there's a notion of smooth functions on a p-adic group that I want to put in here. But in any case, this is something like compactly supported functions. So the kind of idea is that what I want to look is that the analog of loop group representations that we're going to study, and this is going to be the subject of the local Langlands program, they're going to be representations of the loop group, but in what do I mean by representation? In the same sense as when you look at representation of a finite group, you look at representations of its group algebra, which are equivalent. So here, a loop group representation is going to be a module. Now it's going to be a module category over this group algebra. So we're going to look at this group algebra, and we're looking at its module category. So you can ask, what kind of thing is this? So this is sort of a dream world, which we're not ever going to really work in, but this is sort of where we're going towards. So what does this mean? What's an example of loop group representation in this sense? For example, if you have a variety Z on which the loop group acts, then if you look at functions on Z, this will be a loop group representation in this sense. Just same thing, if I have a group acting on a space, the group algebra of the group acts on functions on the space. Maybe another example is if I look at the category of representations of the loop algebra or representations of the Kac-Moody central extension, these are examples of category with a loop group action in this sense. So if this appeared also in Ruminin's talk, that if I have a representation of the Lie algebra, I can think the category of representations of the Lie algebra is acted on by the Lie group. The Lie group might not preserve any particular Lie algebra, any particular representation, because particular representations are not integrable. But the group acts on the Lie algebra, so it takes any representation and conjugates it to a new representation. So this category is a category with an action of the loop group. And this is a way to make this thing precise. So, so now this is a little bit of absurdly large object to study. So what do? We're going to take much, much smaller things. So just like in representation, that we take some kind of invariance. We take some things like highest weights, and we look at representations that have some analog of highest weights. So so we're going to study this crazy world. We're going to take a subgroup K inside of the loop group. And in fact, we're even going to be inside of our favorite subgroup, G of O, or the LG plus. Take a subgroup of G of O, and we're going to look at, we're going to replace this crazy gadget by something a little more manageable, which is Hecke algebra for LGK, which is D modules on double cosets. So now this is something a little more familiar. This is what we did a couple days ago when we looked at spherical Hecke algebra. So the symmetries in the geometric Langlands program were exactly this object when K was G of O. So the idea that K of G of O is kind of the first step of a goal of trying to understand just what are representations of the loop group. So in other words, now the point is that this is a subalgebra, and this acts on K invariance in any representation of the loop group. So instead of studying crazy representation, we're going to take its invariance under our subgroup K, and which hopefully is big enough, small enough so that we actually have invariance, and look at that. So where do we get representations of this? So this thing acts on D modules on Z mod K, where Z is as above. Z is any space with loop group action. If you have a space with a loop group action and you mod out by a bunch of the symmetries, you still have an action of this Hecke algebra. Or it acts on Harish-Chandra modules or representations for the Lie algebra, which are integrable to K. So this is the setting that's being studied by Franklin Gatesbury, trying to understand representations of loop algebras or affine algebras with some integrability condition as modules as representations of a piece of the loop group. Okay, so what does this have to do with geometric Langlands? So what were we doing in geometric Langlands? We were looking at the space of G bundles on a Riemann surface. So we look at the space bun G of X, where X is a Riemann surface. And this, if you look at bun G of X, this was a quotient. This was a quotient of some product of loop groups by product of their positive halves and by some outside part, rational part. So these are, but this is just an extreme way to say that bun G is something of the form Z mod LG plus, well, in lots of different ways. Every time, for every point I take a pick, every time I pick a point, x and x, then I can write the bun G as this thing where what is Z? This is G bundles. This is G bundles with a germ of a trivialization at x. So it's bundles on my Riemann surface where I've trivialized it in the small neighborhood of x. That's a space that carries an action of the whole loop group, but I've gotten rid of the trivialization this way. So that's why we got that if you look at D modules on bun G, they carried an action of these spherical Hecke algebra, Hecke of LG plus, which we identified with representations, the category of representations of the dual group, for every point x and x. So what does the Langlands program tell us to do? The Langlands program tells us that this is just the tip of the iceberg. What we should really be doing, and the real analog of what takes place over number fields, is that we should look not at this space, but we should replace it, that this is just a piece of a much bigger space, which is something like this. So we should drop the quotient by all of the LG pluses. So what we would like to do is these are, so if we look at some kind of functions on this space, the functions we were seeing before are just the ones that are invariant by LG plus at every point. So functions on this is a much bigger space, and functions on this is a subspace, which have this property that every single point, these functions are invariant by the corresponding LG plus. So we don't ever want to look at quite this space, but we want to pick a level structure. What we really want to do is kind of approximate this. And we want to look at some kind of decorated space, bun G of X with a collection of points xi and corresponding level structures. So this is some modular space of G bundles with little bits of trivialization at various points. So we want to say, so this is an intermediate space where we take this thing and quotient out not by all of LG plus, but by various subgroups Ki. And at most points, we don't want to do anything. So there should only be, this should be some finite set of points where we pick extra structure, and everywhere we don't want to have any extra structure. And so this is the real analog of the function spaces appearing in the classical Langlands program. So if you look at D modules on the space, if you look at functions on this space, X with decorations, it now carries an action. Well, it carries an action of the Hecke algebra of LG with respect to LG plus for every x which is not one of the xi. But at these special points, it carries an action of a bigger, more complicated Hecke algebra at xi. Right? Because this space, why does it do this? Because this space is something of the form z mod ki, where z is something on which the loop group acts. So z, I mean, don't do anything else. If you look at moduli space of bundles with the same decoration, except at the point xi, take a full bit of trivialization, or take full formal trivialization rather than just a little germ of it. So it's a space of the form z mod ki where z is something with a loop group action. Therefore, it carries an action of these Hecke algebra. Okay. So what does the real kind of the honest, where honest is called, the word is ramified. So what's the ramified geometric Langlands program study? So the ramified geometric Langlands program says I want to describe, and there's a more precise guess at what this should be, but I want to describe do the harmonic analysis for the space of G bundles where I pick some points and some level structures. And how do I want to describe it? In terms of coherent sheaves on moduli spaces of connections on G check on X with singularities at the points xi. Where did I pull that answer from? Well, we have the spherical Hecke algebra acting at every point except xi. So away from the xi, we have the exact same picture we had before. We have the same commutative algebra of operators, and we know what its spectrum is. Its spectrum is G dual connections wherever I can do these, wherever I have these commutative algebras. So this is the spectrum of this commutative part of the Hecke algebra. And then I need to figure out what to put in at these xi. And to really do that, I need to understand what these more complicated Hecke algebras are. And I will say something about this in the next, perhaps in the most interesting case, after the break. Thanks.